Hi, my name is Hashim, and this is mech2201 assignment for week 2. The question is the question number 5 on our problem set number 2. The question says we have a R34A fluid is contained in a piston cylinder device at T1, which is minus 12 degrees Celsius, and pressure 1 of 0.2 MPa, which is also equivalent to 200 kPa. The fluid is heated at a constant pressure such that the V2 is equals to 25 times the original V1. Heat is then added at constant volume until the temperature reaches T3. So in this problem statement, we can figure out that there are 3 different stages that are going on. Number 1 is we're at the stage where there's only T1 and P1, and then the fluid is being heated at constant pressure. That's the first process that's been happening, constant pressure heating, which leads up to the new volume that is V2, which is 25 times V1. The second process from state number 2 to 3 is a constant volume process where we are still adding heat, but the temperature then reaches T3. That's our stop point of our state number 3. So if we put all that information in our given the schematic, it looks like this. This is our um, piston, piston and cylinder mechanism, and inside we have the 134A working fluid. In the question, it asks us to show the process on a TV diagram, which we will, and it asks us to calculate H1, which is enthalpy of state 1, state 2, and state 3. So these are our findings that we need to do in this question. And I'm just going to walk through this whole solution. So in state 1, we have a temperature, we have pressure, and we don't have the volume, and we don't have H1. In state 2, we don't have temperature, but we know the pressure of P2 is the same as P1 because it's a constant process, constant pressure process. And V2 is equals to 25 times V1. And we will find V1 in order to find V2. In state 3, we know the temperature, we do not know the pressure, and we do not know the volume, but we know that volume is same as V2 because from state 2 to state 3, it's a constant volume process. Again, we don't know the enthalpy of each state, which we will find out in this question as we solve it. So our assumptions, the basic assumption is that the piston cylinder device is stationary. The second assumption is that we treat the compressed liquid state if it's a subcooled or compressed liquid state, and if it's at less than 5 MPa pressure, we treat it as a saturated liquid. So in our state 1 analysis, we know that we have temperature, we have pressure. So let's check for our state from table A1. So we, hold on. So table A11, we can go to table A11, which is supposed to be here, which is our table for our fluid 134A. And we have our temperature at a minus 12. So we go at minus 12, which is over here. Hold on. These are the values that we are concerned with. So we check our Psat at minus 12 degrees Celsius, and we see that it's 185.37 kPa, and we have our pressure P1, which is 200 kPa. So our pressure is greater than the Psat, which means that our state is a compressed liquid. So we treat as an assumption above, we don't have tables for anything less than 5 MPa. So if we treat it as is it was a saturated liquid, whereas a compressed liquid, we treat it as per our assumption as a saturated liquid. So our V1 would be equivalent to Vf, which is the specific volume at saturated liquid point. VF at minus 12 degrees. So if we go back to our table, VF, we have 0.0007499 meter cube per kilogram. And if we go back to our solution, this is what we have from table A11. And similarly, H1 can be found from the table A11, which would be HF at minus 12, which is, we go here, HF at minus 12, which is 35.92 kilojoules kilogram. That is our H1. Let's move on to state 2 analysis. In here, we have from our question, basically, as much information we have pressure, which is P2 at 200 kPa, because it was a constant pressure process from 1 to 2. We have the same pressure as we had in state 1, which was 200 kPa. And the V2 we know from the question is 25 times V1. And state 1 analysis, we found V1 to be 0.0007499. We multiplied that by 25 to get V2, which is 0.0187 meter cube per kilogram. So let's check for the state. For state, we go to A12 because we have pressure this time, we don't have temperature. So we go A12. This is our A12 table. And we go back, what pressure do we have here? 200 kPa. So we go back here, we find 200 over here. This is 200. So we go back here and we have V2. So we go back here, we look at the VF and VG values, and we see that our V value lies between these two over here. If it's in between, we know it's a mixture. So we know that if it's a mixture, we need to find X, which is the quality, that how much of that mixture is the vapor and how much of it is liquid. So in order to find that, we use the formula that we learned in class for X. X is the quality, which is V minus VF over VG minus VF. We take these values of VF and VG from this table at 200 kPa, which is these two values right over here. We plug them in, and the V value we already have, V2 of 0.0187 meter cube per kilogram. We use that to get our quality X, which is 0.181. So using that, we can just substitute it into the enthalpy formula for quality, which is H2 is equal to HF plus X times HFG, or the difference between HG or HF. Again, these values can be found at 200 kPa from table A12. I'll just show you over here. So HF is this, HG is this, and HFG is provided to us to be 206.03. Going back, we plug that in to find we plug that in into our formula over here. We calculate it, and our H2 is 75.72 kilojoules per kilogram. Moving on. Now we are working with state 3. For state 3, we know that the temperature is 80 degrees Celsius. That's good. And we have volume V3 is equal to volume of V2. Why is that so? Because it mentioned in the question that from state 2 to state 3, it's a constant volume process. So our V remains constant. So V3 is equal to V2, and we just found that V2 is 25 times V1, and we found V1 in state 1 analysis. So just forwarding that onto here. So V2 is 0.0187, which is same as V3. Now we do the check for this state. We go to table A11 and look at 80 degrees Celsius. Okay, table A11 is here, and 80 degrees is right about here. So what other information do we have at 80 degrees? We have our V. So we go back to our this, we check VG. So our VG is 0.006436. And we know that our V is 0.0187. So our volume is clearly greater than our VG. So if it's greater than VG, we know it's a superheated state. So if it's superheated, what do? We go to table A13. And when we go to A13, we have to start looking for our volume value, where we can find our volume value. So table A13, which starts here. So we know we are at 80 degrees, and we know our volume. We check each row at 80 degrees. We don't find anything that suits our values. We keep on continuing until we end up over here. So at 80 degrees, we find that our value of volume, so this first row over here and this first row over here, is volume per just meter cube per kilogram. And our value lies between 0.0205, and it's less than that, but it's greater than 0.017023. And our volume is 0.0187, which is clearly between the two values. So what we do, we apply this interpolation formula. We need to find H3. So we have V3. So we use H and B values to find our, and H values are right besides this. This is our H values, H and V's. So we go here, the values we're going to be using is this value 308, 311, this, and these. These four values that we're going to be using are inputted, this 311, 308 in H's values, and then respectively the volume values as V3, and we just fill up this formula, and by interpolation we get H3. So now we have H1, H2, H3, which satisfies our B part. Now we need to show this whole process of state 1 to 2 to 3 in a TV diagram. How do we do that? So this is how our TV diagram looks like. We start here at state 1. We know it's a subcooled liquid. That's why it's on this left side of the TV diagram. And outside that, there's our curve, a saturated curve. So at -12, we are at subcooled liquid. We add heat, but we know it's a constant pressure process. So it continues along this line, which is P2 is equal to P1. They're the same pressure. So state 1 and state 2 lie on the same pressure line. So it goes from here to here. Now we know that from state 2 to state 3, it's a constant volume process. What constant volume means is that we have volume on our x-axis. So if it's constant, that means it's going to stay at this value. So the only way it can move is up and down. And we are adding heat, the temperature is going to rise. And it's rising. We know it goes up to 80 degrees Celsius from the question. So we have a straight line going upwards towards state 3. And we know it's a superheated state. So it lies beyond the saturated line curve over here at P3 line. So that's the whole solution of the question, and that is how you solve this type of question. And how do I stop?